about algebraicity of Shafarevich. Great, not so much. Before I forget, I'm going to say that I joined work with Goethe and
Okay, so I want to start off very simply with the very general statement about the topology of algebraic graph. Okay, so let X be a normal algebraic graph. Complex algebraic. Okay. And suppose we have a representation of its fundamental. And so maybe I'll say and here, but I'll probably forget that soon. So I'm going to see the fundamental with respect to the classical topology with some representation. Okay, and of course, representation of the fundamental group we can think of as a local system. Say in a sort of a C local. Okay. And the question I want to ask is, can we sort of algebraically extract the subvarieties that aren't seen by this local system? Okay. So to put it in a slightly different way, here's the question. Can we contract all the subvarieties on which this local system has finite monotone? Subvariety of X, for which being restricted to the finite line. Somehow these are the subvarieties that are not seen by the local system because the local system is sort of not so complicated if it has a finite monodromy, and we want to sort of extract all those. Okay, so let me make this a bit more precise with the following definitions. Okay, so I'll call a morphism F from X to Y is a V Shafarevich morphism. Or no, now often abbreviated morphism too. If it satisfies the following properties, so if first, well, we want to somehow specify enough properties so that this map will essentially be unique. And if this map contracts all the subvarieties on which this local system is finite, I can sort of post-compose with any other finite map, and that'll also do the trick. So I want to prevent myself from doing that. Okay, so we should ask for y to be sort of normal. I'm going to leave a space here, and we also want the function field extension to the other variable. We want ky inside of kx algebraic. Somehow this is saying that the fibers are connected. I think this is not a problem map, so I can't literally say that, but this is saying that the generic fiber is. Sorry, this is my, I'm going to blame this on my jet lag, but in this question, I want to contract all the subvarieties of this finite monodromy, but only those subvarieties, right? Okay, so contract precisely those. What is the solution is. Okay, so that's the first condition to prevent you from sort of post-composing with finite maps. The second condition is just going to say V is pulled back from Y, which means that it's trivial in the files. V pulled back from Y. Okay, now you might immediately have a problem with this, because I'm talking about, I'm admitting the possibility that there are subvarieties from which V is finite monodromy. but somehow this map that I'm starting to define, V is pulled back from Y, so it's trivial on the fibers. So seemingly I'm not allowing for any finite monodromy. And that's where the space comes in. I should allow Y to be a finite monodromy. Because then on fibers, it will have finite monodromy. Right. It's not a big deal. The best possible statements. What you want to do. Okay, and so now V is trivial on the fibers. And now I want to say that somehow the only things, all of the subvarieties on which V is finite monodromy are contained fiber. Okay, so for connectivity, if I have some orbital in V to X, which has the property that the pullback of V is trivial, then G factors to a fiber. Factors through. Again, let's take a second to, I said trivial here, and yet over here I was talking about contracting subvarieties in which there's finite monodromy, and it's the same, because if ever I have a connected Z mapping to X for which the pullback is finite monodromy, I can just take a finite tile covered Z, and I'll get a map with the same image for which the pullback of the local system is trivial. Okay, so contracting images, varieties on which it's V is trivial is the same as contracting ones for which images of varieties on which it's finite.
Okay, fiber, is that supposed to be connected, or is that implied, or is that not implied?
No, that's conditions.
All connected,
Well, the channel fiber is connected.
oh, yes.
And it emits a like relative specification for which it has to make fiber or not.
When they want to see you proper, is that
Nope.
so say if you have an entire curve inside your X is already,
The entire curve?
yes.
No. Everybody's on the break. Yeah. Sorry, is that what you're asking?
Yeah, I mean, if Z is an affine line, it's somehow embedded in your X, and it should be also the fibers, right?
Yeah, that's right. Okay, cool. Well, let me make a couple of remarks. So one of them I already made, to make it again, that if you don't like this, I mean, this is the best way to formulate this problem. If you don't like the fact that Y is allowed to be a Munster stack, it will be the case that if this morphism exists, then after a finite tile cover of X, it will also exist for the pullback local system, and the Y will now be just an algebraic space. Okay, so you don't have to worry about stacking this if you don't want to, but then I have to allow myself to move up along a finite cover of X, which is kind of a slightly nastier state. So that was my first remark. Zero remark. One thing, if the Shafarevich map exists, we're in particular saying that the local system V is pulled back from algebraic variety on which it's infinite monodromy on every subvariety. Okay, and there's a name for that. In particular, if it exists, V is what's called large. Large means that V has infinite monodromy. On all positive dimensional subgroups. Okay, so the existence of the Shafarevich formalism is somehow the same as saying, is every local system pulled back from an algebraic variety on which it's large. Okay. And sort of conversely, if I find an algebraic variety on which my local system is large, it can't be pulled back from any sort of further along any further algebraic map. Sort of this largeness condition is telling you some minimality of algebraic varieties on which this local system is pulled back. Second remark is I can do the same thing, and it will actually be pretty important for some collection of local systems. I don't have to work with just a single local system V. I can take any set of local systems. Okay, so I do the same for a set sigma of local systems, which I want to think of as a subset of the C points of the Betty stack. So this is just the stack of local systems. The C points are the complex local systems. So for any subset of local systems,
Finite subset or?
any subset of local systems, in which case we call it a sigma Shafarevich. Now, this is important. This is why I phrased the definition this way, because you might have, for a collection of local systems, you might have come up with a different definition, just motivated by this question. And what's important about this definition, in the case that I take a set of local systems, is I'm contracting subvarieties on which sigma is uniformly high, right? Because they haven't all been trivialized from the same atomic type. Okay, that's different if sigma is some big set of local systems, different from contracting subvarieties on which each guy in sigma becomes finite. So it's just a smaller one. Okay, remark 3 is that the existence of this thing is kind of unreasonable. Because like this is some purely topological condition, and I'm asking for it to be achieved by some other great math. Well, you would imagine that might not happen all the time. That would be pretty reasonable. So this is unreasonable to expect. Except, there are two main reasons you might expect this to be true. So the first is sort of motivated from the Shafarevich. Why these maps are called Shafarevich. The Shafarevich conjecture is the following. It says for smooth projected, okay, the universal cover as a complex analytic space has some special form, and is what's called holomorphically convex. Okay, so more concretely, that means that the universal cover at tilde admits a complement to a sign space. Call that Y tilde. Okay, so this is just what it means to be holomorphically convex. Why is this at all connected to a Shafarevich map? Well, now we can do the kind of following tricky thing. We can take this map from X tilde to Y tilde, then we can quotient out by the action of pi 1. And now we get a map like this. And this map has the property that every local system is called back by construction. Okay? Because the sort of fibers of this map can contribute to the fundamental. So this will be is sigma Shafarevich morphism. Or does sigma take into all? And some of this, like the history of the Shafarevich conjecture sort of existed before. And then Kolar, in an attempt to sort of come up with a strategy for proving it, realized that one consequence of it is the existence of this Shafarevich map. And then he kind of tried to invert the problem and first show the existence of Shafarevich. Okay, so somehow, as far as evidence for an unreasonable expectation is concerned, the outlandish conjecture is not great. So let me give you a more concrete evidence for why you should expect this thing to exist. The second reason you should expect this to maybe exist, which also hints at why Hodge theory could be relevant, is because we have a main example of this sort of object existing. And that's the following. Suppose that this local system V underlies an integral variation of Bakker. Polarized Okay. Maybe I won't remember what this is, but essentially that means that the local system is a Z-local system, and there's some sort of holomorphic filtration on the associated vector bundle that's okay. And the main point here is that it gives me some additional data for which I can sort of track the moduli of that data in the physics of B. In particular, I get a period map from X to the moduli space of pod structure up to integral automorphism. The punchline of what I'm about to say is that this morphism is actually going to realize this Shafarevich mechanism. Okay, so why is that? Well, the sort of good news is that an integral variation Hodge structure is isotrivial, meaning the Hodge structure is not varying, if and only if the local system has finite moduli. Okay, so an integral polarized Hodge structure is isotrivial if and only if B is finite moduli. Okay, so we've at least produced a map that contracts exactly those subvarieties on which B has finite moduli. Okay, so that's starting to look good. The sort of bad news is that this is sort of a fundamentally analytic construction. I mean, already the space is a very analytic space, and sort of the variation of Hodge structure itself has to simultaneously be the holomorphic structure and the topological structure. So it's going to be non-algebraic. Okay, so the bad news is that B is analytic. Okay, but with a strong caveat, which is that it's analytic, but it's not actually so bad. So if X is projective, well, we constructed an analytic map from a proper variety. Gaga tells you that it's algebraic. Gaga says image of B is algebraic. So we simply produce an algebraic morphism by mapping to this analytic space, which contracts all subvarieties in which you finite moduli. And now in the general case, the same is true. We just have to sort of replace Gaga. Gaga. Same philosophy as a number of years ago, plus the result Bruno, the sort of definability of the period. Okay, so I will come back and talk about what these words mean, but at the moment you should just think of them as sort of some version of Gaga that gives you the same conclusion without the properties. Okay.
But can I ask you?
Yeah.
I would say,
Yes.
there's still the issue there also. Why it's open on Taiwan?
Yeah, absolutely. Yeah. No, here, this is a purely analytic construction thing, so.
You didn't address it, but
Sorry, and here I'm assuming X is projected.
ah,
So in that case, it's the same. Okay, that was the bad news, but then actually we are granted with even further good news, which is that the period domain has some nice curvature properties. In particular, the distance function for the point has some positivity, which allows you to show that the image of this map on the universal cover is Stein. That's the image of phi. I take the universal cover is Stein. Somehow we're not only from period maps are we seeing the Shafarevich map, but we're at least getting some hint of why something like the Shafarevich conjecture should be true, because we're at least producing a map to a thing with universal cover is Stein, and from which the system is pulled back.
You want to normalize them?
Right?
I mean, the image has no reason to be normal.
That's true, but you're saying with my current definition.
Yes.
Well, it's still true that it's Stein.
No, I agree.
Maybe not now, but maybe later. Yes. Okay, cool. So. Okay, so let me just say in words, I already mentioned some of the history. Okay, so I mean now for period for integral variation Hodge structure, we're in good shape. Now we go back to the case of what about a general local system where there's no Hodge period in sight. Okay, so let's go back to B general. And like I said, there's some history here. So already, hold on, going back to the 90s, it produced some birational version of this Shafarevich map. With a birational version. And somehow their strategy goes by sort of cycle spaces. I mean, you have a natural equivalence relation that you want to plot out by, namely the equivalence relation of being connected by subvarieties along which the local system has finite non-coordinate. Okay, and you can make sort of a birational version of the quotient by that equivalence relation, which actually is the quotient at sort of a very general point. So it's kind of very similar to the MRC quotient. The map you produce from this does the correct thing outside of a countable union. Okay. And then towards the sort of late 90s, a number of people.
This graph on paraconstruction works if you fix an infinite sigma, or
If you fix the what?
if sigma is infinite.
I think, I mean, actually what they do is just for subgroups of pi 1.
I think it's
They don't actually don't need both. So Ramachandran, Sarkov, and it's good. I did the case on that projected. This was sort of around in the 2000s. And this is where they start to show how Hodge theory, even though there's no Hodge theory, it's just a local system, they show how you can sort of still use arguments from non-abelian Hodge theory to construct this Shafarevich map. And in fact, using that together with sort of concept, and then able to prove the Shafarevich conjecture when you have a faithful representation of in the projections. With the condition is the so-called having a linear pi 1, meaning having a faithful representation. And then maybe I'll just make one remark. So actually, the kind of means of proving the Shafarevich conjecture in this case is kind of what I was already saying up there. Once you construct the Shafarevich morphism, the end game is just to show that the universal cover of the image Y is Stein. Okay, so what it implies in the Shafarevich conjecture is that if a projective X has a large local system, with then the universal covers. That's and finally, so this is the sort of story of the projected case, and sort of more recently, an analytic construction of the Shafarevich map has been made. So by Greenbaugh and by Deng and Young. Construct Shafarevich map. Analytic. And you can see that already, I mean, if we're already using pouch theoretic techniques, it's kind of reasonable in the non-proper case that it's an analytic construction, because once again, it's going to use pouch theory. And you know, here, if X is projected, then it doesn't really matter because you can always appeal the gut. It's price for the quarter choice, I think.
Is Greenbaugh and then humanoid or on the reduction presentations?
Yes, they only do it with that. Yeah, that's the kind of ignoring that. Yes. So strictly speaking, this construction is for semi-simple. Okay, so now let me get the name here, but I spend the rest of the time talking about it. Okay, so theorem one. Is that an algebraic Shafarevich map for any sigma exists. Okay, so there is algebraic sigma Shafarevich map. So Y always. Even better, Y is quasi-projective. This is you know, again a very non-obvious fact. We're saying that you know, for any local system, for any collection of local systems on an algebraic variety, there is some minimal algebraic variety from which they're all pulled back. And such that you know there are no subvarieties left on which this collection sigma is not complicated, and moreover, this Y is quasi-projective.
Before it was a really long start.
Oh yeah, good point. The course, moreover, the course Y is quasi-projective. Happy to think. So
Is X projective?
okay.
So is that X projective?
Sorry.
Is a X projective again?
This part.
No, X.
Oh, X is an algebraic space. Right? I mean, it's certainly not projected. Certainly quasi-projective, but even actually it works for any algebra. If you want, you can take it.
But then Y is not projected.
No, it is. Now, Y is just always, the course of this Y is always quasi-projective. And regardless of what algebra it is,
One normality.
sorry?
Is X still normal? Because it's set in
X, I mean, yes, X should be normal. It's actually not gonna matter, well, yeah, but the way I set up the definition, let's just assume everybody. Y is definitely. Okay, theorem two. Is sort of, there's a version of again, the linear Shafarevich conjecture, in this case of quasi-projective varieties. So once again, as I was kind of sketching up there, once you know the Shafarevich graph exists, the Shafarevich conjecture, as long as you have a linear fundamental group, is basically the statement that this Y is signed universal color. Okay, so that's the statement. If E is large, then X tilde is quasi-Stein. Okay, what is quasi-Stein? I mean, there is more than Stein. Okay, so why is this quasi here? Well, that's the best you can hope for in the following example. Okay, like, A2 minus the origin. It's simply connected. Maybe I'm doing this the wrong way.
Yeah, that's right. It's simply connected, it's not covered itself.
No, but it doesn't have a.
That's the panorama.
Yes, yes.
No, but it doesn't have this large condition. Okay, well, let me give this example anyway, and then I'll say the reason you should allow for sort of being significantly open is the following situation, where this is not Stein, but this is Stein,
Yes, you can take any surface with large local system, then take out the point. You can take a surface with large local system, take out the point.
yeah, right, sure. You can take, yeah, I mean, yes, the point is somehow you can always delete on a smooth thing, you can always delete points and you'll destroy Steinness, but you won't change the fundamental group. You're not going to change the largest definition, but you're going to change the Steinness conclusion. Okay. But, strictly speaking, this is the counterexample with different stable or whatever. Okay, cool. So
the main point here is X is also, because X doesn't have to.
right, yes. So here, in both of these statements, the point is that X is now just any algebraic space, whatever. You want to take a quasi-projective product. Okay, so. And so I guess it's, I think, just like up there, let me the corollary to sort of connect it back to the Shafarevich projection. If X has a faithful representation of Taiwan, then the universe of color is quasi-homomorphic. And again, I mean, this is just a corollary. Once you know the topic, and so in a sense, it's a version of those. And then the quasi-homomorphic convection is the best you can hope for the same reasons. You can delete stuff without changing the fundamental group, so you can destroy either the Steinness of the image or the properness of the map.
But I don't understand your Shafarevich reduction, they define it, it's not proper anymore.
Yeah, that's right. That's right.
So when you say quasi-homomorphic convex, it doesn't mean it's proper of a quantity.
No, it means it's a Zariski open in a homomorphic convection.
I
So it could be holes in the fiber or in the thread.
and it's relatively proper.
Yes. Well,
I mean,
no, it's just a Zariski open hole. Okay, great. So let me describe a little bit about how the proof of this goes. And I first want to describe a construction of the analytic construction of the Shafarevich map. But somehow that's where we see Hodge theory. And at the moment, there's no Hodge. Okay, so let's talk a little bit about the construction of the Shafarevich. And here I'll be following the part. Okay. So let's remember what we're trying to do. We're trying to contract images of maps from varieties on which my sigma becomes trivial. Okay, so the sort of the test morphisms are morphism G from Z to X, okay, from a connected Z, for which if I look at the pullback map on the Betty stack, the sigma goes to just trivial morphism. Okay. Now, nobody says sigma, that these are the only local systems that become trivial. Okay, these are just the one by one. Okay, so the first observation is without changing the Shafarevich map, I can immediately add some more local systems. Namely, I just take the intersection over all such maps of all local systems that become trivial. Let me give that a name. Sort of a tautological construction. I'm going to define the Shafarevich closure to just consist of all local systems that become trivial under any map that sigma becomes trivial. Okay, so sigma Shafarevich closure is just equal to the intersection over all maps connected things for which the pullback is trivial of the full inverse image of trivial. So everything that becomes trivial over all maps that sigma. Okay? This might consist of more local systems. But now the point is this pullback functor preserves a lot of extra structure here. And whereas my sigma was just some completely random set of local systems, this Shafarevich closure is also going to have all the natural structures that the Betty said. Okay, so that's going to be important. Okay, so we've already seen some of the structures that Betty stack has. So non-abelian Hodge theory tells you there's a C-star action. Okay, so that's the first point. Point number one is that non-abelian Hodge theory, which sort of has many names associated to it, we at least say sort of Simpson in the projective case and Montezuma in the non-projective case. Tells you that there's a C-star action that this pullback functor respects. Okay, and of course, and the C-star action, moreover, fixes exactly the complex variation question. Okay, well, nothing to support the complex variation Hodge does more trivial representation. This guy is C-star fixed. So it follows that this pre-image star fixed for every G. So this Shafarevich closure is C-star fixed. Non-abelian Hodge theory tells you that this is C-star fixed. And moreover, the sort of T goes to 0 limit of the C-star action always exists and always gives you a variation of Hodge starting from any local system. And that immediately implies that sigma Shafarevich contains some variations of Hodge. Contains okay. And as soon as I have a variation of Hodge structure, I have a period.
When you say fixed, you mean stable. Like is there?
Oh yeah, sorry. It's C-star Thank you. It's closed under the C-star action. So in particular, the limits, if I take the limit of any point, as t goes to 0, it's contained in here, and it gives me a variation of Hodge. Okay, so for every complex variation of Hodge structure, again, a period map on the universal cover, some period domain. And this period map, when we index it by V, has the property that it contracts all the subvarieties on which V is unitary. Okay? That's kind of the complex variation Hodge structure version of the statement that an isotrivial integral variation of Hodge structure, integral variation of Hodge structure is isotrivial if only in sign and monodromy. In general, a complex variation of Hodge structure is isotrivial if and only if its monodromy is unitary. Okay, so that's number one.
This is polymorphic or
No, the field is that one. No, and it tracks infiltration, which is just a holomorphic object inside of the So I mean, it's on the universal cover, but it's a map to a flight, right? Holomorphic map.
so here all the V's could be unitary.
Sorry?
All the V's could be unitary.
All of these could be unitary, indeed, yes. So it could be, this could be the trivial. You can track it. Okay, what else? What other structure does this Betty stack have? Well, I mean, the character variety is defined over Q, right? Because it's just representations of some finally generated group. Okay, so this is defined over Q. The trivial representation is a Q point. That means the inverse image of that for each one of these G's is a Q subvariety. Means the intersection of all of them is a Q subvariety. Okay, so the fact that this is all defined over Q means that the Shafarevich closure is defined over Q. Okay. So in other words, from nothing, I produced some Q local systems that become trivial in this map, on the fibers of this map. Therefore, Shafarevich contains Q local systems. There's kind of a parallel story here. In the case of the Q local system, there's a map I can produce whose fibers are exactly things along which the local system becomes an integral local system. Okay, so this is a little complicated because the target of that map is a building. But let me just say it nonetheless, it's a map like this, which contracts stuff along which B, I didn't give it a name, creates two local systems, let's say B. B, along which B is integral. And I should also say the names here, many more names. This kind of this harmonic map to buildings is sort of pioneered by Gromov and Schoen. And then where are those names? Oh, it's Sarkov and Zulu, mostly in the projected case, and then much more recently, and then in the non-projected case by many people. That's a thing. Oh, never mind. Okay, sorry. You probably didn't read those, but at least I can out loud.
Why did she start?
Sorry, say again?
What, is G star defined with Q? So
Is what star?
the map G star.
G star. Oh, yeah.
Oh,
I mean, it comes from a map of fundamental groups. Right? So if you take the character variety, they're just finally generated groups, and you're looking at the variety of matrices that satisfy some relations. Everything's defined over Q in the map. Not always happen.
But sorry. Now these are just local systems, or are these just local systems or VHS?
No, this side is not talked to this side yet.
Okay.
So this here I produced variation quad structure in this Shafarevich closure. Here, I say I, but I mean this is not nothing I did. So the construction of and this side is just producing Q local systems inside of the Shafarevich closure. There might be no overlap.
I think you said it, but can you explain again why the desization points are very. How do you get them?
Oh, why is it true?
Yeah.
Oh, so I mean, sorry, why is the C-star fixed thing? Well, this is sort of seen on the Higgs bundle side, right? The C-star action on the Higgs bundle side just scales the Higgs field, and it being stable, at least gives you that the Higgs field is no potent, and actually gives you more. It gives you that there's like a grading with respect to no potent, and Simpson shows that corresponds to a complex variation function. There's always the associated grading of a complex variation. Yeah, sorry, I kind of threw that out. This is
Kind of magical, getting in for almost nothing.
yeah, absolutely. No, this is the magic of Simpson. It's not a reflection. They're produced right into the model structure out of thin air. The other board.
so the very quad structure is not necessarily polarized.
Well, okay, so this is just terminology. A complex variation quad structure is sort of by definition polarized. Okay. So there's a flat emission form floating around that satisfies the required positivity condition. The sort of only thing that's missing is the integrality. That's sort of, that's where this is going to be. Okay, so there's of course much more argumentation involved in what I'm about to say, but kind of somehow the idea is that I produced a bunch of maps which contract things along which these variations of Hutchins are unitary. And I produced a bunch of other maps which contract things along which these Q points are integral. And somehow if I put these two maps together, I'll get something for which all the local systems in sigma are unitary and integral, in other words, finite. Putting these together, 1 plus 2, you get a map of the universal cover to well, a bunch of period domains. We sort of product all of these together. Cross, well, I'm actually not going to put this down, so this is not something I want to dwell on. There's actually an algebraic variety you can put here, such that the algebraic fibers of the map to S are the same as the the fibers of the algebraic map are the same as the algebraic fibers of this map. That's some technicality that I don't want to get into. But putting these two sides together, I get a map from the universal cover, polymorphic map, to a product of stuff, such that the fibers of the first guy sort of makes everything unitary, the fibers of the second guy makes everything integral, and then therefore the sort of fibers of this map make everything finite. It's the idea. There's something to check. Okay, and moreover, one can show that this map has compact connected components of the fibers. Okay, so there is a sign factor.
Sorry, can you repeat the main property of that map? Because I'm a bit lost. I mean,
Yeah, well, there's a jump here, but this map has the property that everybody in sigma when restricted to fibers becomes uniformly finite. Everybody, all of sigma becomes uniformly finite. That's not 100% obvious. Somehow the idea is like this is making it unitary, this is making it integral.
yeah, but it's for different.
It's for different sets of things, but somehow yeah, that's the idea. Okay, so now we have this analytic map, which has the property we want. It contracts the things along which the all the local systems in sigma are finite, and we can just take the quotient by pi 1. Okay, so this gives me a map. Gives me a sigma from X to something I'll call curly Y, which is the sigma Shafarevich. And that was a bit of a before constructing this map, but I wanted to at least describe where the Hodge theory comes from. This kind of miraculous fact about this Shafarevich closure sort of automatically being kind of stable under all the structures that the Betty stack has, in particular the C star action and the and this kind of.
What is the property of the fibers? So there's some compactness there.
Yeah. So I said it verbally, but I didn't write it. The property that this map has that allows you to take a standard fiberization is the connecting components of the fibers are sufficient for this time. Right?
But I understand you take your X, you multiply it by just to define space. Yeah, the defined space should be given by any Shafarevich map.
Yes.
So how can the connected components of fibers be complex?
Well, the connecting components of the sorry, it's not okay. So let me answer that question after. You have to, in order to get the properness here, you or the compactness of the connecting components, you need to first pass through a partial magnification of X, and then. Okay, great. Okay, 10 minutes. All right, great. So I want to describe somehow how the definability shows up here. So we've constructed this map, the Shafarevich map. I mean, analytically, again, this is Bruno-Barb and Benjamin Lewis construction. And, but it's like obviously a very analytic construction. Okay, I took this complicated analytic map on some cover, which happened to have compact connected components of fibers. So I could produce this kind of factorization and then descend it. But I mean, those fibers, I mean, there might be like, you know, the number of components of fibers could be judged. Okay. So somehow the bad news, if I want to view this whole story as sort of parallel to the story of taking the period map of a variation of Hodge structure, the problem, the bad news, is that this map does not descend. Okay, there is no sort of period map from X to like some kind of quotient with this by easy. You know, what kind of showed up in the case of the period map. And that's because, you know, part 2 tells you that the fibers of the map to S have an integral structure. That integral structure is kind of changing as I move around D, so there's no global integral structure. So there's no real natural group acting discretely here such that this quotient makes sense. Okay? So if I want to algebraize this map, I'm kind of in a tough situation because I don't even have a reasonable space that I'm matching to that I can take the image of, right? I mean, to apply Omega Gaga, you want to take the image somewhere and then do something to show that that's algebraic. But there isn't even an image we found. We've produced this y by Stein factorization. Okay. So maybe I'll skip over a couple things because there's a point I want to get to. But the good news is that O minimal Gaga plus something will allow you to finish for algebraize this y. So O minimal Gaga. So it doesn't just finish the story because I don't have this this image. But O minimal Gaga does reduce you to following. So this is sort of theorem 3. Stein factorization exists. In the final analytic. Okay, so let me not 100% explain why you can reduce this. It's certainly reasonable because here I'm taking a sign factorization and sort of that was the problem in algebraizing y. And somehow, if this map lives in this definable analytic category that I haven't told you anything about, as long as I can Stein factorize it, then it shouldn't be a problem. I should be able to, you know, form this y tilde in this other category, and then I should be able, and then O minimal Gaga will tell you that that this is algebraic. Okay, so now let me take a couple minutes to actually tell you what these words mean. So you should think of. I know Bruno alluded to it a bit, but somehow the point is that an O minimal structure tells you a notion of tameness for both sort of subsets of C to the n and for functions. Okay, let's not get into, you know, what the notions of tameness are, but as far as subsets are concerned, you should imagine taking like real semi-algebraic subsets of C to the n. Okay, those are sort of tame subsets. Okay, so it's something a little more general than just algebraic subsets of C to the n, but something not as crazy as might be allowed in the analytic category, take arbitrary. Okay. And a definable analytic variety is nothing more than you take, you know, in these sort of tame open sets of C to the n, you take 0 sets of tame holomorphic functions and you glue them along tame holomorphic maps. Okay, with one extremely important caveat. The atlas I use to do this gluing had better be a finite cover, because if I take an infinite cover, I'm going to lose sort of all the tameness that I worked so hard to make precise in C to the n. Okay, so these definable analytic varieties are, you should think of them as sort of spaces which have a finite cover by these sort of tame subsets of C to the n, and such that the Bluing maps are tame. Okay, great. And so, what does openable Gaga allow you to do? Let me say it a little more precisely now. If ever I have a proper map from an algebraic variety to a definable analytic variety, in the sense I just defined, openable Gaga tells you that this image is algebraic. Okay? This uses sort of results of Artin and the fact that if you have sort of tame coherent sheaves on an algebraic variety, they're forced to be algebraic. That's kind of the whole point. So the global tame objects in this definable analytic category are then forced to be algebraic. That's why you are then able to prove something of the form, you have a map from an algebraic variety to a definable analytic variety. Then the image has to be algebraic. You should view the tameness property as just systematically preventing essential singularities from ever happening. Okay? And if essential singularities never happen, then if you have a, if you have a coherent sheaf in this definable analytic category on an algebraic variety, you can imagine that the sort of sections extend meromorphically, and that's enough to say that they extend algebraic. They do some algebraic rectification, and that means it's algebraic. I got it. That's sort of a good cartoon version of sort of what this definability is actually about. Okay, but that kind of raises, it kind of gives a hint at why definable Stein factorization in the definable analytic category is a little bit tricky. Okay, so this is a bit tricky. Why is that? Well, we all know how to prove Stein factorization. We prove it the way Grauer proved it, 60 years ago. And he proves it using cohomology, uses the proper image theorem, showing that the push forward of a coherent sheaf is coherent. Okay, and that proof is just straight up not going to work. Okay, and the problem is that coherent cohomology is really poorly behaved. Coherent cohomology is bad. And why is it bad? It's bad because there are these kind of important points. There are no acyclic colors. Let's go back to how I define these things. For an algebraic variety, you have a finite cover by affines, and in affines there's sort of Steins, so they have no coherent homology. Analytically, okay, maybe you're not covered by affines, but you're covered by small balls, and those are Steins. They have no coherent homology. Okay, but if I'm in this like middle ground where I'm not covered by affines, but I can only use finite covers, then the sort of open sets I'm allowed to use in any cover are gigantic. Okay, so there's no reason I should be able to produce a finite cover of a random definable analytic space by stuff that has no coherent homology. And so I can't apply that homology. And I was looking forward to, I really wanted to prove Stein factorization for it. Because, so the way we get around it, we have to come up with a new proof of Stein factorization. It's 2024. New proofs. Whatever, that's fine. But it's cool. It's like a geometric proof, right? Because you can't use cohomology, and okay, you could. That takes you back to the 60s, and then you can look at Stein's original proof, but that uses sort of finite space techniques, and that's no good. Because sort of infinite dimensional spaces are also bad from this perspective of tame geometry. So you have to produce some geometric construction of Stein factorization. And let me just, in 30 seconds, tell you sort of what the point is. I mean, what is the Stein factorization? You want to sort of find polymorphic functions. So I have a proper map. I want to produce the Stein factorization. That means I need to produce sort of polymorphic functions on X locally on Z, which separate out the connected components of the files. Okay. And if you think about it, that's really a statement about producing polymorphic functions on Z with sort of prescribed monodromy, namely the monodromy of the connected components. Okay. And phrased that way, it's kind of a difficult problem, right? I mean, how do you produce even locally analytically producing sort of showing that there are polymorphic functions with prescribed monodromy. But it gets even worse in this situation, because now our open sets are gigantic, so their fundamental groups are huge, and I still have to produce sort of global homomorphic functions. Moreover, ones that have this tangent property, that have a prescribed moduli. And just to give you a hint of what the key step of the argument is, and like tell you how to reduce that. You use algebraic geometry to produce those functions with complicated monodromy. You do some reduction, blah blah blah. At the end of the day, you can show that the sort of functions, the monodromy you sort of want to produce, can be realized by a family of curves. Okay, so you reduce the problem to pulling back functions from MG, where you know that you can build algebraic functions that have a prescribed monodromy, and that's how MG enters the story. I think I'm contractually obligated to have mentioned MG points. So now that I've done that, I want to stop.